So, electronic spectroscopy of a molecule, they are basically, as we have seen, this total energy E total, or let us write in terms of centimeter inverse, E total equal to E energy of electronic energy level plus vibrational energy level, energy of the vibration and energy due to the rotation. Okay. So, this will be the states of molecules. This will be the states of molecules where this electronic energy levels are accompanied with the vibrational and rotational energy levels. Okay. So, for a particular state, it will give the energy of the state as a sum of this individual energy of electronic, vibrational and rotational. Okay. So, now when there will be transition from one state to the another state, so now one has to remember that electronic transition from one state to the another state. So, one state means here electrons or molecules in a state where its electronic state, vibrational state and rotational state is defined. Now, from this state it is going to the another state. So, another electronic state, another in that electronic state another vibrational state, in that vibrational state another rotational states are there. Okay. So, transition between two electronic energy level for a particular these two energy levels. Okay. So, this this energy, so now this molecules, so it has come from one energy level to the another energy level. So, if it is, so their energy difference will be energy difference or energy of the spectral lines will be, so del epsilon is total of the spectral lines equal to, so if we take that these energy levels, their transition between these two energy levels. So, if we take this electronic, it is in a electronic state is E double dash, okay, and transition from this state to the another electronic state, this it is E dash, E electronic, E dash. Okay. So, their energy separation, this energy separation will be, I can write E electronic dash minus E electronic double dash. Okay. So, this energy separation, now each electronic state, it will have this vibration, due to vibration it will have vibrational states, and that vibrational states are if I draw with other color. So, this will be one, the second one is this, third one is this, okay, because this vibrational energy level what we have seen that is basically vibration. So, let me draw. So, this is the vibrational energy level, and here this for these electronic states, these vibrational energy levels are like this. Okay. So, here so if we give these states V double dash, that will be, this is 0, this is 1, 2, 3, 4. Okay. Similarly, this in this electronic state, so if we vibrational state, if we write V dash, so V dash it will be, I think it's 0, 1, 2, 3, 4, 5, etc. Right. So now between this so transition from this electronic state to this electronic state, now is transition from which vibrational state to the which vibrational state here. So that also one has to see, and then each vibrational energy level, again it is associated with the rotational energy level. So this their energy are small, so each one will be again so their spacing decrease, basically their spacing decrease. So each one will be, yes, each vibrational level will be associated with the rotational energy level. So this one can write J double dash equal to say 0, 1, 2, etc. Okay. Similarly, here also there will be rotational energy level, there will be rotational energy level. So here J dash, one can write J dash, that is 0, 1, 2, 3, etc. Okay. So this basically it's here, this basically it's here, right. So so your energy, so since, so here let us see first this only considering the vibrational energy, neglecting this rotational energy separation. So that's why if we tell that, so let us see this electronic spectra, that's basically electronic spectra, this core structure of electronic spectra or vibrational core structure of electronic spectra. So now we are seeing the basically core structure, vibrational core structure, yes. So this vibrational of electronic spectra, basically vibrational core structure of electronic spectra. Electronic spectra. Okay. And then later on we will see this rotational fine structure of electronic spectra. So at the moment we are neglecting this rotational fine structure. So that means, say this is, we are not considering these energy levels, we are not considering this energy level. Okay. So in this case, this total energy, it's basically this plus, I think I can use this another color. So this energy, so here you will see this for vibrational energy, that is omega E bar V plus half. So here we will write V dash. So V dash, here also we write omega E dash. Okay. This minus, not yes, minus. So I can write basically this. Okay. minus of omega E dash chi E dash V dash plus half, okay, then close second bracket, okay. So this is the vibrational energy, say in one of them, okay, V equal to 0, 1, 2, 3. Now it is going from here to here, so minus of omega E bar this double dash V double dash plus half, okay, minus omega E double dash bar chi E double dash V double dash plus half. I think this is square. I think this one is square. Hopefully, this yes, I think so. This V plus half square, I guess. Yes, it is square. I think this one is square, this one is square. So here also this is square, okay. So then, okay, so this change will be basically due to the vibration, okay. So and this rotational part we have neglected for this case, and you can tell that this the energy of the spectral lines, and if we consider the this selection rule, del V selection rule is del V, this change is now it is not in same electronic state, you know. So it's one electronic state to the another electronic state. So del V basically V dash minus V double dash, okay. So that will be say 0 plus minus 1 plus minus 2 etc. Okay. So if you consider the transition, now in generally the spectral lines, two types of spectral lines we tell that one is absorption spectral lines, another is emission spectral lines. So there are some advantages considering the absorption spectral lines. One advantage is that I can consider that this before transition, the system, the molecular system, it is at a ground state, okay, lowest energy level state. It is in lowest energy level of electronic energy as well as vibration energy. So we can consider this initially molecules are in this energy, right. Now if you put light on it, okay, or if we excite it, so it will go from here to the higher energy state, okay. So the spectral lines will see that it's two ways we define them. One is progression, another is progression, and another is called sequence. Okay. So what is progression? Progression is basically if this transition starts from here, so this is the ground state. If transition starts from here, V double dash equal to 0, and it is going to here V dash equal to 0, then V dash equal to 1, V dash equal to 2, V dash equal to 3, V dash equal to 4. Okay. If it is, its transition is like this, then we label these spectral lines. We label these spectral lines by using V dash, V double dash. Okay. That means these spectral lines, whatever the spectral lines we will see, say, let me just, the spectral lines we will see these spectral lines here, these spectral lines, yes, here, here, here. Okay, I think it should be closer, it should be closer. So like this we will see spectral lines. So these spectral lines here, we, I think I will remove this, then this will be labeled using this 0 0 0 0. This will be labeled as a 1 0. This is 2 0. Okay. This is 3 0. Then this is 4 0. So this way these spectral lines are labeled. Okay, and this is called this progression. Spectral lines, this vibrational core structure, whatever it is, this type of spectral lines is called progression. Okay, because here you can see this this V dash, it is in progression because this 0 1 2 3 4, so it is increased by 1. Okay, so that's why it's called this spectral lines are called progressive spectral lines. And another type, as I told, that is called sequence. Okay, it's called sequence. So basically it's like this. So here to here, then here to here, then here to here. Okay, then here to, so as a sequence. So 0 to 0, 1 to, yes, 1 to 0, 1 to 2 to 0, 3 to 0, okay, 4 to 0, like this, or this yes, I think this difference, this is coming as a I think this it's a sequence. The difference, it will be like this, either 0 1 2, okay, or -1 0 1 2. Okay, so these are the, as if it is following the sequence. Okay, sequence. Okay, so this del V here, it's I think I will tell you this. I think let us finish this. I have to. I think let me finish this this progressive one. Later on, I will tell about this sequence one, because I have to draw this spectral line separately. Then it will be easy to understand. So now here what I have shown you, these spectral lines, there are many spectral lines and their separation are decreasing, right. Now, question is that here whatever the spectral lines we are seeing, whether what about the intensity of the spectral lines? All spectral lines are same intense, or there are some spectral lines only we can see, all spectral lines we cannot see. So, let us see what about the intensity of the spectral lines. So, this intensity of the spectral lines in case of sequence, in this case, what will be the intensity of the spectral lines? Intensity of the spectral lines, vibrational course structure of course. So, in this case, what is the intensity of spectral lines? Okay. Or spectra, intensity of spectra, whatever we have seen here spectra, what about the intensity of that one? Now, intensity, it is so intensity means the transition probability, right. So, here if all atoms or molecules are in this state at ground state, okay. Now, when there will be electronic transition, okay. So, now molecule, so from this state, from this electronic state, it will go to the another electronic state, okay. So, then it is in a different situation, right. It is in a different situation, x omega, we have seen that I have written this omega e and chi e, x e, okay, anharmonicity constant. So, we have written dash, also we have written double dash. So, that means, so in this state, in this electronic states, their vibrational frequency and their anharmonicity. So, there for in this state whatever vibrational frequency and anharmonicity constant. So, that will be different in this another electronic state, okay. So, that will be different in another electronic state. So, that means its vibration states will be affected. So, it will be different vibrational states, okay, sets of vibrational energy levels, okay. Now, so from here, when from this electronic state, it is in a particular vibrational state. Now, what is the probability to go from here to there? So, this is the electronic state that is fixed. Now, what is the probability to go in this vibrational energy state, or this vibrational energy state, or the other vibrational energy state, okay. So, what is the probability? So, that will decide the intensity of the spectral lines, because here all are same, or we consider, that is why we consider the absorption spectral lines. So, in that case one can easily assume that all molecules are in a lowest energy state, either electronic or this vibrational. Now, from here it is going to the another electronic state. When it will go in another electronic state, it will be in different vibrational configuration. That means it is vibrating, two molecules, two atoms in a molecule, they are vibrating. So, energy levels of this vibration, it depends on the separation of these two atoms, right. So, separation is changing, their energy are changing. So, they are in different, they will be in different energy states, okay. So, when it is here, as if vibrational, so they are vibrational state, they are in equilibrium distance because it is V double dash equal to 0. So, they are in equilibrium distance. Okay. So, that is the vibrational state. In this electronic state, electronic double dash. Now, from here it is going to the another electronic state E dash, E electronic dash, that is fine. Now, when it is going to E electronic dash, in that electronic state, what is the what will be the vibrational state of when it is in this electronic state? What will be the vibrational state means what will be the separation of these two atoms, okay, in the molecule. Okay. So, that means here I can, so here we can tell that this there, so one molecule, one atom is say fixed. Okay. So, when their separation is changing, so their energy will change, right. So, this is the equilibrium energy. So, from here it is changing like this, and from here it is changing like this. Okay. So, so this is the separation corresponds to this vibrational level. Now, its separation is this. So, now separation is changing. Okay. So, other one is vibrating, right. When it is, its energy will be same. Okay. In this state from equilibrium it is vibrating. So, it's this the energy, this is the energy states, energy level. So, this way it is the different energy level. It is the different energy level, right. Now, similarly here when it is in this electronic state, just electronic transition, then exactly that time what is its vibrational state. Okay. So, I think I need this space. So, in this case, so if we consider, see in this electronic state it is the same way. If I consider that, so that we have to consider it can be in any states, but I do not know, it can be in any states. Okay. So, if I consider that after this transition here it has come here, so electron, this vibrational state in this electronic state is this V dash equal to 0. Okay. So, if so, so then again if you draw this, I think I should draw following the symmetry. Okay. So, actually I have drawn here this one, this for 0 state energy is not 0. So, that is why generally we write the energy of this, yeah, it is here, energy is here basically. Okay. When atom is here in this molecule, so its energy state is this. Okay. So, that is the V equal to 0, that is V equal to 0, V double dash equal to 0. So, this yeah, then 1 2 3. So, here it is V dash equal to, this one is V dash equal to 0. Okay. So, now if we consider that this will be the energy state, vibration energy state in this electronic state, if we consider, then there will be all transitions, as if the way I have told this, all transitions are possible. But here Frank-Condon, so this there is a principle, it is called Frank-Condon principle. Frank-Condon principle, what it is telling? It is telling that this one may tell that it is initial state. Now from initial state it is going to the excited state. So during transition, electron transition and this vibration all the time it is changing, right? All the time this vibration, this position of the, that's why it is vibration. This vibration, this molecule atomic distance between these two molecules is basically changing with time. Okay. So transition from this electronic state to another electronic state. In case of absorption spectra, it is fine, all the molecules are in this lowest vibrational state. Now during transition, after transition, it can go. So this vibrational state of this excited electronic state, this vibration state. So it is all the time it is vibrating. So during transition, okay. So this vibrational state can be this one, okay, because all the time it is changing, it can be any one of them, right. So it can go from this transition, vibrational transition, it can be from here to here, it can be from here to here, it can be from here to here. That's how we have drawn like this, okay. So but this principle is telling, it is considering that electronic transition is so fast compared to the vibrational transition, okay. So one can consider that this during this electronic transition, whatever the molecular vibration state here and here, during this electronic transition, so it will see that state only, okay. So another state, to change to the another state, vibrational state, whatever the time it is taking. So before that time, that time is higher than this just sudden transition, electron transition. It is so fast, this transition will not see change of the vibrational change, okay. So as if whatever it will during transition electron transition, whatever it is here, so whatever the position of the vibrational state, it will see that one and it will go there, okay. Now if this is the situation during electron transition, now it is telling, one can tell that this, what is the probability here. So spatial probability, if we consider this for harmonic oscillator, if you draw the wave function or probability function, it varies like this, I think this way. So for 0 point, so this wave function is like this, okay. For next one, this probability, you know the wave function is like this, in this wave function is like this. The second, next one, wave function will be like this, okay. Now probability is chi square, so probability will be like this, yes, probability will be like this, probability will be like this. So here, yeah, probability will be like this, okay. So what is the probability? So this, in it is telling that this molecule, this its states is here at this distance, and here this probability to stay at this distance, okay. This is the highest probability, okay. This is the highest probability, and here if you go higher and higher, you will see. So this probability will not be, I think it's smaller, okay. So you will see this, if you go higher and higher in the vibrational level, you will see this this probability is shifting towards the edge. So at the edge of this curve, the probability will be maximum, and that's the classic. So from quantum mechanics you can say like this, and classically you can say that, you see this it's oscillating, vibrating, right, okay. So in turning point it will spend more time, because it is going and then coming back, it is going and then from here coming back. So turning point, this molecule atom will spend more time, oscillator will spend more time. So to find the oscillator at this position, okay, is maximum, and that's what. So it is going towards classical concept for higher vibrational level. So initially it is in middle, highest probability, and then this probability shifting towards the edge, okay, towards the turning point. So if you consider this probability, so in this case here is the highest probability, and if this is the position of this excited state, so these lines, so transition between these two, so 0 0, that will be maximum. Transition from here to another, you see here, if we go this way, so it will see this as if this vibrational state is like this. So here going there, it is probability is less, as for here, okay, probability less. In middle for other energy levels, this probability will be less, okay. So that means it will go, but probability less. So the intensity this of other lines 1 0 2 0, this probability will be less and intensity will be less. So this will be most intense line, and in this case that's why one can tell that this is the intensity of 0 0 spectral line, and the intensity will decrease for other, okay. So this is for as for this Frank-Condon principle. So this intensity varies. So this one state I have shown you. So if it is so, I think I will continue the discussion, it will take some time. So here I have considered one situation. So if situation is different, okay, so if when this electronic transition is there, so atomic this position in this excited state or vibrational that distance is not this one, it is different, either higher or lower. So considering that one, what will be the transition probability? So in that case we will see this not 0 0, it may be 2 0, may be this intense line, okay. So I think we need to discuss more. So I will continue in next class. Thank you.